So coming back and leaving these terms up that we looked at in the last video, we need to make some sort of approximation. And one of the most important ones is the Born-Oppenheimer approximation. And this approximation has to do with the relative speeds of electrons and nuclei. Electrons, as you may recall, are much, much lighter than nuclei. So the mass of an electron is about 1/200th of the mass of a proton or neutron. And so even in the case of hydrogen, where the nucleus is only a proton, the electron moves much, much faster than a nucleus does because the mass is so much larger. And this discrepancy only gets bigger as we get to bigger nuclei as we continue down the periodic table to things like helium or something like uranium, where there's a huge difference in the mass between the nucleus and an electron. So the Born-Oppenheimer approximation is that we can treat nuclei as being fixed relative to our electrons. So basically, the electrons will adjust to what the nuclei are doing faster than the nuclei can kind of keep track of it. So, if your bond length changes for whatever reason, the electrons will basically immediately, we treat it as being instantaneously adjust to the change in the potential energy before the nuclei can basically react to that. So what does that do in terms of these terms that we have present? So what we can do is we can treat this as two separate problems. So we can take these first two kinetic energy terms that involve our nuclei, so these two terms here, and ignore them. All right, so we can say that, so to a first approximation, and you can't see that behind me, so we ignore the motion of the nuclei and just worry about the electrons. Right? And so then all of our terms involving electrons, now there's still a lot of them, are the things that we need to solve. So all of our other terms that we have involving electrons are what we need to solve. And in practice, what we do with this is, say for a diatomic molecule, is we will fix the bond length. And so in our units above, that would be R12, or sometimes we'll write this as big R. This is sorry, that shouldn't be 1, 2, that should be AB. Right, so our distance between our two nuclei will give this notation big R, meaning the bond length, right? So we'll fix that bond length and then solve the electronic part of the Hamiltonian, of the Schrodinger equation. And we can do this by ignoring what's happening with the nuclei. All right, solve the electronic part, find energies, energy levels, wave functions, all that good stuff. And we can find those solutions for a particular bond length. And then what we'll do is we'll change R by a little bit and solve again. And this will give us a map of the energy of our system as we change the bond length. And basically we'll get a plot that looks like the energy of the system versus the bond length. And so because we use the Born-Oppenheimer approximation, we can treat each of those changes as we can basically ignore what's happening with the nuclei and just solve the electronic part of the problem. So, in this particular example, it eliminates two of our, kinetic energy terms that we need to worry about when we're solving. And generally, this is a very good approximation because of the relative masses of nuclei and electrons.